Welcome to The Explainer. Today, we're diving into a brilliant piece of engineering that was actually inspired by our own bodies. It's a device that's surprisingly simple, incredibly powerful, and honestly hidden in plain sight all around us. It moves everything from life-saving medicine to, nacho cheese, with a kind of purity you just can't get any other way. So let's get into it. All right, first let me ask you something. Have you ever wondered how you can swallow a sip of water even if you're hanging upside down? I mean, it's not gravity doing the work, right? It's actually a super clever pump that's built right into your body. And this pump relies on a process called peristalsis. It's this, wave-like squeezing motion that your esophagus uses to push things along. Each squeeze moves a little bit forward, making sure everything goes in one direction. It's what engineers would call a positive displacement system. And this, right here, is the light bulb moment for our entire explainer. What happens when you take that brilliant biological idea and you turn it into a machine? Well, you end up with one of the most versatile and reliable pumps ever invented. Okay, so let's zoom in a bit and see how this mechanical mimicry really works. And you'll see it's just so elegant in its simplicity. When you break it down, there are really just four essential parts. You've got the drive, that's the motor, the power. Then there's the pump head, which is just the housing. Inside that, you have the rotor, which has these little rollers that spin around. But the real star of the show, the absolute key to the whole thing, is the flexible tubing, because it's the only thing the fluid ever touches. And here's that peristalsis in action. As the rotor spins, one of those little rollers squeezes the tube completely shut. That makes a perfect seal, trapping a little pillow of fluid. The roller then keeps moving, pushing that pillow forward. And right behind it, as the tube springs back to its normal shape, it creates a vacuum that just sucks more fluid in. It's this constant cycle: compress, push, relax, refill, over and over. Now, that complete squeeze has a name. It's called occlusion, and it is the secret sauce. Seriously, because at least one roller is always pinching the tube shut, there is no way for fluid to flow backward. None. This is what makes it a true positive displacement pump. You don't need any extra valves or seals that could break down or cause contamination. But this is where the story gets really interesting. Because the very thing that makes this pump a work of pure genius is also the source of its one big weakness. It's this fundamental trade-off, like a design paradox, that's baked right into its DNA. Just look at this. It's fascinating how the pros and cons are literally two sides of the same coin. The purity is amazing because the fluid only ever touches the tube. But because it moves the fluid in those little pillows, the flow isn't perfectly smooth. It pulses a little. It's gentle enough for live cells, but tough enough for concrete. But all that squeezing means the tube eventually just wears out. And it's super low maintenance, but its power is totally limited by how strong that tube is. And this quote just nails it. It all comes back to this one simple principle. Containing the fluid entirely inside that flexible tube is the source of all its greatest strengths and its biggest challenges. So that brings us to the most critical point. If the tubing is the source of both the genius and the flaw, well then choosing the right tubing isn't just important, it is everything. It's the heart of the whole system.
See, you can't just grab any old piece of tubing. Oh no, you have to consider a whole checklist of things. First off, is it chemically compatible with what you're pumping? Will it just dissolve? Does it have the right inner diameter for the flow rate you need and the perfect wall thickness to fit the pump head? Then you've got to think about its hardness, what engineers call its durometer. And that's a tricky balance. You want it soft enough to last a long time, but hard enough to handle the pressure. Get any of this wrong and you're headed for failure.
And that's exactly why there's a whole menu of materials to choose from. Silicone, that's your go-to for anything ultra-pure, like in medicine or biotech. PVC is kind of the low-cost, reliable workhorse for general use. TPV, like Norprene, is the marathon runner. It just has an incredibly long life, perfect for heavy-duty industrial jobs. And when you're pumping something really nasty, you'll want a fluoroelastomer, like Vitin, which can handle almost any chemical, even if it doesn't last as long mechanically. And I mean, the difference in lifespan can be huge. We're talking night and day. If you're running a really harsh, high-pressure application, you might only get a couple hundred hours out of a tube. But in a light-duty, low-pressure setup, that tube could easily last for 1,000, maybe 2,000 hours. It all comes down to the job it has to do. So how do you know when it's time to swap it out? Well, you have to be a bit of a detective. You gotta watch for the signs. If you see any visible cracks, that's a big one. Or if you notice your flow rate is starting to drop. Or sometimes you can even hear it. The pump might start making a duller, kind of slapping sound. That's your cue. If you replace it too early, you're just wasting money. But if you wait too long, you risk a big, messy failure.
All right, now that we know how it works and what makes it tick, let's zoom back out, because this simple little pump is an absolute workhorse, and it's hiding in a shocking number of places all around us.
In medicine, its role is absolutely critical. I mean, we're talking life or death. Peristaltic pumps were inside IV machines, dialysis units, and even heart-lung bypass machines, where they gently circulate a patient's blood without damaging the cells. They're used for filling vials of vaccines with incredible precision and for moving delicate cell cultures in labs. Here, that purity isn't just nice to have, it's non-negotiable. But they're not just in sterile labs. They are out in the world doing all kinds of jobs. They dose the flavorings into your favorite soda. They add chemicals at water treatment plants. They can pump super abrasive stuff like concrete slurries. And yep, that pump dispensing the hot nacho cheese sauce at the stadium, you can bet that's a peristaltic pump, keeping things clean and moving right along. So you see, it doesn't matter if it's saving a life or serving a snack. The core principle is exactly the same. It's a simple, tough, reliable way to move a fluid while keeping it completely isolated and pure. And get this is not some newfangled idea. It has a long and amazing history. In fact, the legendary heart surgeon, Dr. Michael DeBakey, developed a version of this pump for blood transfusions way back in 1932, while he was still in medical school. How incredible is that? Which really leaves us with one final big question. The peristaltic pump is just a perfect example of biomimicry, of looking at a brilliant idea in nature and engineering a solution. It really makes you wonder, doesn't it? What other simple, elegant biological ideas are out there, just waiting to inspire the next generation of powerful machines?